All right, thank you for introduction and thank you for coming to my talk on Sunday in such a nice weather. All right, so let me, where's the joke? All right, let me start with some classic things. So we're gonna consider the hypersurface as D in projective space, the n-dimensional project space. So this is a smooth hypersurface degree D in Pn, and we suppose the n is 2. All right, and we know this famous theorem, so which says the Automorphism group of this hypersurface is exactly same as the Automorphism group of the Pn, which fix this hypersurface, unless Nd is I think 2, 3, and 3, 4. Right? So this is a very basic and a very famous classic statement. So to prove this statement, if n is this Automorphism group of the hypersurface. No, it's not complement. The Automorphism of the Pn, which fix the hypersurface. So they are same, right? Unless this condition, like unless the Nd is 2, 3 or 3, 4. So to prove this, so if n is 4, then this hypersurface has the picard number 1. So you can use the hyperplane section to show this. If n is 2 or n is 3, then you can use the canonical divisor or anti-canonical divisor. But in this case, you don't have you have the trivial anti-canonical, the canonical divisor. That's why you have an exception here. More or less. All right, so today we're gonna reinvestigate this phenomena inside out. So question of today, for us, is the following. So when we consider the Automorphism group of the complement of this hypersurface, so and we consider the same Automorphism group here, which is the Automorphism of the Pn, which fix this hypersurface. When these two groups coincide, that's the question to consider today. Okay. All right. So the motivation of this question was originate from the conjecture raised by Gijatullin. So conjecture by Gijatullin, I think it's 2004. So he conjectured the following. So he considered cubic surface in P3, and he claimed this. He conjectured the Automorphism of the complement of this cubic surface is exactly the Automorphism of the P3, which fixed this hypersurface. Okay. All right. So here, I don't know why Gijatullin chose this cubic surface, but so let me give you a reason why. My reason why he supposed to choose this cubic surface for this conjecture. All right, so let's consider the situation. So now, suppose you have automorphism of this hypersurface. I mean, the complement of the hypersurface. Let's say in general, and this. Okay. All right, and suppose the alpha is the honest this is the automorphism of the Pn outside of this hypersurface. So you may consider this guy as the bidirectional automorphism of the Pn. Okay, and suppose this is the honest bidirectional automorphism of the Pn. So this is a bidirectional. Let's say honest. It's not automorphism of Pn. That's what I'm saying. Not biregular, yeah. Huh? Okay. All right. Then thing is this Pn has the picard number 1, and the alpha is the biregular outside of the hypersurface, but the alpha is not the biregular whole space of the Pn. That means this alpha must contract the hypersurface Sn, right? So picture is like this. You have Pn, and you have this bidirectional automorphism of Pn. You have Sn, Sd is here. So you reserve this the bidirectional automorphism. So you get this, right? So this guy should be contracted. That means that you have some exceptional divisor here, and that means this exceptional divisor, Sd, must be a bidirectional to this exceptional divisor, right? So that means, so we are working on the smooth case. I mean, the ambient space is smooth. So that means so your Sd must be ruled, right? Your exceptional divisor is ruled, so like this. So you can say if your hypersurface, if Sd is not ruled, then that means that this automorphism, two automorphism groups coincide. Pn and Sd, right? So here is the simple things. So if D is strictly bigger than N, this thing happens, right? Yeah, smooth. Everything is smooth so far. It's not the case, but some special cases we'll talk about later. Okay, and so here is my table. So here, so this is a degree, and this is the dimension of the project space. So here, so two groups coincide. Then you got this circle. Right? All right, and we have this famous theorem by Skopsky and Manin. So it says and Skopsky and Manin, I mean, they originate from starting from the Skopsky Manin and like Puklikov and the like Chersov and the Kola and the Pernet about the variational rigidity, which case, I mean, when the degree same as the n and the n is 4, then this SD is variational super rigid, variational rigid, variational rigid, which implies SD is not ruled. Right? This is by Skovsky and Manin and Puklikov and Depernes and Chersov and Kola and so on, right? So we've got circle here along this diagonal, right? All right, and we also have this. We can consider cubic 3/4, which is non-rational, right? But the cubic case is special. So we know the cubic 3/4 is non-rational, but if the cubic is ruled, then that means they are rational, right? Because we have this Castello-Berger, I mean the rationality theorem. So P1 plus some surface, and this surface must be a rational. So this is Clemens and Griffiths. Correct. So S3 is not ruled. Right. So we got sucker here. Right. And also we have this theorem by Kola. If SD is very general, and if satisfied this inequality, I think D is 3/2 n minus 2, then SD is not ruled. All right. So but it's not for every. So we have this line on here. So this at some point is over the diagonal. So you have some area which generically covered. Right? But this area is unknown. I mean, this point is we don't know yet. All right. And for lower degree, I mean the degree 1 case is let's look at the other side. So if degree is 1, then that means automorphism of this complement. It's just the automorphism of the Cn. This is a huge infinite dimensional group, but this Pn and this S1, this is the Pgn, which is finite dimensional, so they are different. Right? So here, here doesn't work. You fix this.
Okay. Somehow it's very different.
Okay. Yeah, yeah. But anyhow, like this is a finite dimensional and this is infinite dimensional. All right, and all right, and degree 2 case. All right, and we consider this. All right, you remove the quadratic hypersurface, and you consider this. All right, again, this is finite dimensional, but this is not finite dimensional. So I will explain why this is the infinite dimensional group. All right, so yeah, for all n. But for simplicity, we consider the case here. For simplicity. But yeah, it holds for every n. All right, the reason is this. P2, or let's say S2, is the main reason is that the reason why these two groups are different is that this complement is cylindrical. So the meaning is the following: it contains a Zariski principal open subset U, which is isomorphic to this type of the variety. So for some affine variety Z. All right. All right. So this is the picture like this. So you have this is your P2, and you have this conic S2. All right. All right. We'll consider a line which tangent to this conic. All right. This is a tangent. All right, you first remove this line, then you get the A2. And this S2 will become this parabola, right? So picture is like this. So you have, okay. So this, you have this, this is a C2, right? And you have this parabola, which corresponds to this S2. But you translate, then you can cover this C2, whole C2, right? But you just remove the original, like this parabola. Then you get this is C cross C star, right? So this is the cylinder, right? This is fine, and this is a C, right? All right, then what you can do with the cylinder is the following. So you can then on U, so U, this is a C cross Z, right? Something like this. All right, then you can define this C plus action on U. All right, fiber-wise. Yeah, along C. All right. Then this C plus action defines the locally nilpotent derivation. Locally nilpotent derivation on this ring in here. All right. All right, and we require this Zariski open subset to be a principal. Then this principal condition allow us to extend this locally nilpotent derivation to another locally nilpotent derivation on this whole space, P2 minus S2. Okay. All right, and then we return back. So we get the C plus action on C on this space. So there is a one-to-one correspondence between this C plus actions and the locally nilpotent derivation on this ring. So whenever you have the non-trivial C plus action, then you get the non-trivial locally nilpotent derivation. Whenever you have the non-trivial locally nilpotent derivation, you get the C plus action. So, and then like this principal condition allows to extend this locally nilpotent derivation to the regular ring of this guy. So that means, so this C plus action defines along the fiber, but you can change this C plus action by this regular function on Z. So this whole group contains in this automorphism of this. All right, so that's why this guy is the infinite dimensional. So these two groups are different. So you get this. Huh?
Wouldn't you instead use the fact that P2 minus S2 is a homogeneous space for SL2 action?
I cannot hear.
There is a natural SL2 action on P2 minus S2. For which it is homogeneous. Yes, your U is just the variance of 2. Yeah. So this is probably gives you a signal.
But yeah, this is
in this case, you can actually construct the partially transform the complement. In this case, yes, but it's
high dimensional case. All right. So we have this the difference. I mean, if degree is 1, 2, we get the difference, and if degree and this area, we have the coincidence, right? So this cubic case right here, Giza-Tulling's conjecture here. So it's a very subtle point. So here we know everything. Yeah, this is the Giza-Tulling conjecture. I mean, for the this, and this position is this lattice point is the Giza-Tulling's conjecture. So below this line, so everything is okay, and this we know the answer. But this way, I mean, with this is depends on the big theorem. I mean, the Clemens and Griffiths. And this, we don't know. I mean, we vaguely know about this, but it's not complete answer. So this is a very, it looks very, I mean, among this is the easiest case, but still we don't know the answer, right? By the way, so here, so this difference depends on the cylindrical things. So if this guy is a cylindrical, then we can say these two groups are different, right? So let me put remark here. So if Pn minus Sd is cylindrical, then automorphism of the complement, and the automorphism of the Pn and Sd, they are different, right? All right, so but indeed, I will show later, but indeed, P3 minus S3 and the Giza-Tullins case, this is not cylindrical. In some sense, it's sort of evidence for the Giza-Tullins conjecture. All right, so we have this remark, and based on this remark, so we can generalize the Giza-Tullins conjecture in the following way. This is another generalization of Giza-Tullins conjecture. All right, so here is a situation. So we consider surface, their feature surface, a differential surface of the degree, the anti-canonical degree is at most 3, with the at most Duval singularity. All right, so if degree is 1, then our weighted project space is the 1, 1, 2, 3, as the Vanya explained before, and degree 2 case, the S is the P 1, 1, 1, 2, and this is if S is the smooth, then this is the Giza-Tullins the case, right? P3. All right. So, and this is the degree is the sextic. This is the degree 6. This is the hypersurface of degree 6, and this is the hypersurface of degree 4, and this is the degree 3. All right. All right. And then, like in this situation, you can ask the same question. When these two guys are the same, the group of the complement of this surface, and thus automorphism of this weighted project space which fixed the hypersurface. Right? Okay, so this is the generalized Giza-Tullins conjecture. All right, but okay. We had this remark about the cylindrical case. So if this complement is a cylindrical, then there's two groups different, right? So let me propose the weaker version of the question above. So you can ask when this this complement is cylindrical. Okay. All right. So we're going to consider this question, the weaker version. All right. And all right. So to consider, to attack this question, we need the another notion of the cylinder. So let me define. And this notion was introduced by Kishimoto and Prokhorov and Zeidenberg. So it's about the polarized cylinder. All right, so this is the definition. And this is due to Kishimoto, to Prokhorov, and Zeidenberg. All right, so the following. So X is a normal projective. And the H is an ample divisor on X. All right, then we say, we define the H cylinder on X. This is a Zariski open subset U such that satisfy the following two conditions. The first condition is U is the isomorphic to the complement of the support of the some Q effective divisor as an effective Q divisor, Q linearly equivalent to H. And the second, and U is a cylinder. That means it's a C times some affine variety Z. Affine variety Z. If two conditions satisfied, then the U is called the H cylinder.
Why do you say that U is isomorphic?
You say this? If you like, you can do it. Yeah, just take it. All right, so let me give you a simple example right here. This is a typical example. So here, let's say this line is L, and there's 2, and you have the P2 here. All right. All right, and then I explained the complement of this 2 divisor is a cylinder. So isomorphic to the others. All right. And this L plus S2 is even linearly equivalent to the anti-canonical divisor here. All right. So that means this complement P2, the support of this L plus S2. This is anti-canonical cylinder. Right? All right. All right, so when I start this talk, I start with the automorphism of the hypersurface, all right, from the inside. So let me introduce the theorem by the Chersov and myself and the one. I think it's 5 or 7 years ago. So it's about the cylinder on this Del Fischer surface case. So here, all right. So here, our surface, and here is it's like this. The condition is like this. All right. All right. What it proved is the following. So this S contains minus and the anti-canonical cylinder if and only if contains the no anti-canonical cylinder if and only if the following conditions satisfy. If the degree 1 case, for the degree 1 case, the S allows only A1 singularity, A2 singularity, and A3 singularity, and D4 singularity. If it contains the other type of singularity, then it will contain the cylinder. If S3 square, the degree is 2, then the S allows only A1 singularity. Right? And if cubic case, if we consider the cubic case, then S allows no singularities. Oh, all right. I cannot hear it. What was your question?
This is singular. No,
No.
not the complement.
This is the cubic itself. But will be later. All right, so we are looking at the hypersurface, the Del Fischer surface. So this theorem says the the S contains the no anti-canonical cylinder if and only if this condition satisfied. So about the singularity conditions. Okay. So for example, the smooth cubic case, it does not contain the anti-canonical cylinder. Right? That's what this theorem says. Okay, let me. See. Okay, so the idea of this proof. Let me briefly explain how to prove this. So for this direction, all right, let me start the opposite direction. All right, so what you have to prove is suppose this S contains the anti-canonical cylinder. Then that implies you're gonna have just some Q effective divisor. Q effective. The effective Q divisor. D, such that first of all, D is the Q linearly equivalent to the minus K, this first condition, and the second is this pair SD is not row canonical. It's not row canonical at some point P on S. And 3, this guy, I mean, you consider this a support of D, and you consider this the hyperplane section by the tangent hyperplane section. Then it does not contain this. If you have the minus K cylinder, then you must have this effective divisor, D, which satisfies these 3 conditions. But for example, I mean, this is for the case when the degree is 3, but the situation is similar in the other cases. And then, like, I mean, this property comes from the existence of the cylinder. But the property of the cubic surface does not allow us to have such divisor. So we can show that this is impossible. This is impossible. Okay. This is the brief idea of this direction, and this direction. And suppose you have the singular point in P, S, and this is your P3. All right, and then you project from the P. This is a singular point, and this is a P2. All right, and this is the birational map because this is a singular point and this is a cubic. Right, and the birational, and then you reserve the no, this is a projection, and but the birational. So you reserve this indeterminacy. So you get as tilde, and here this is exceptional divisor, and let's say this image is C. Okay. All right, then outside of this C and the outside of this point, I mean S, they are isomorphic, right? All right, and roughly speaking, like this C depends on the singularity types, A1, A2. No, wait. No. F depends on the singularity types. This is the conic, or like 2 lines, or this is 2 lines, or this is double lines, right? And this is a C, and you add one more here in this case, and I add one more, and I add one more. Then you get this complement will be a minus K cylinder. So, and then you can move the cylinder structure to here because this is biregular outside. So this is so that means whenever you have the singular point on the cubic surface, you can construct this cylinder. So that's the idea. All right, and so this singular artist, if point P, in this case A1, A2, I mean okay. All right, here. So for example, like degree 2 case. So here, the 1, 1, 1, 2. Right? And then here in cubic case, you project, right? So we have the same idea. So you project to the not 1, 1, 1. So here 1, 1, 2. And if P is not if this is not the A1 type, then you get always the birational map. And in degree 1 case, if P is not this type, then you get the birational map. I mean, same situation. So that's why you can construct always. All right. So, and then based on this theorem, so we have this Rusty, I think Rusty here. We have the following theorem, which corresponds to this automorphism of the complements. So now we look at the complements case. So this is a theorem. By Charles of Blows and myself. All right. So Fs contains a minus K cylinder. Okay. If and only if this complement is cylindrical. So this is the bridge from the this inside to the outside. So once you have this K cylinder inside, and then you can define the cylindrical structure outside. And whenever you have the cylindrical structure outside, then you can have the minus K cylinder inside. So the idea of this proof is it's the same. So you can what you can do. All right, let me skip the proof, but it's very similar and very geometrical. All right, so we have this theorem, right? So and then due to the what theorem, so we know when this S has the cylinder exactly, right? So this is the right. So the corollary. So the complement to S is the cylindrical. It's not cylindrical if and only if S satisfies this condition. Right? So in particular, in smooth cubic case, it does not have the minus Kelly cylinder. So that means this complement of the smooth cubic is not cylindrical at all. All right, so it means this. If in this case P3 S3, if this is the same, if this is the same, then that means our cubic is smooth. So this Giza-Tulling's conjecture is very fragile. So if you allow the singularity on the smooth cubic, then the Giza-Tulling's conjecture is wrong. So only the smooth case. Only smooth case we can expect this Giza-Tulling's conjecture is true. So here is the new conjecture, which is the generalized Giza-Tulling's conjecture. So this is the conjecture. So automorphism of this complement is same as the automorphism of the P fixed the S if and only if S satisfies the star. All right, this is the singular case. All right, and here is the one remark. in this case, I mean, if we have this degree 1 case, 2, 3, and if S is smooth, then this conjecture is true. This is due to the conjecture holds. Due to green anchor. He proved he considered, I mean, he proved the smooth the double Baronet cone, which is sitting in this 1, 1, 1, 2, 3, and there is degree 6, right? And this is smooth. What he proved is the variational automorphism of this 3-fold is the same as the automorphism of this 3-fold. So using this, you can prove this case. I mean, this conjecture is true for the smooth Delphi surface of degree 1. Okay. All right, my time's up, so let me stop here. Thank you.
Questions? I have few comments. One comment that Grinenko proved this result while he was postdoc here for 1 year. His contract was for 2 years. How long term? Grinenko? So this result improvement was good in that. I think he was supposed to be about 2 years. His girlfriend didn't get the visa. So he, after 1 year, went.
So after it's better, you don't compare this.
Yes. Now, yeah. So this is Karin originated. I have no questions. Okay, if no questions,